Let's start. I would like to start with giving you a short recap of the setup for a stochastic differential equation, which is here on the slide. And consider this as a definition. That's what you define the stochastic differential equation to be. So you say that if you have a Gaussian white noise, which is defined by a probability distribution function, then you consider a class of stochastic differential equations given by the first equation, where you say that the differential change in a random variable is a drift term and a kind of diffusion term, where the prefactor of diffusion term is a configuration-dependent function. So that defines it, but not quite, because if you integrate this differential equation, then you get a relation like so, where formally this is well defined. That's just a standard Riemann integral over a known function a. But this here is not a standard Riemann integral. It's an integral over a stochastic differential variable, which are our Wiener increments given by the Gaussian distribution. So you need to define what you mean by that. And it's defined in this way. So this integral over the Gaussian increments is defined as a limit of finite increments that are again Gaussian distributed with a dt replaced by delta t. And then you have a choice. The Gaussian increment evaluated at time ti, so let's say at t2 here, is multiplied by the function that you have there at some other time t2 bar. And t2 bar you can actually put at t1. You could put it in the middle or anywhere here between t1 and t2. Any choice is possible. And two choices have a name. The choice where you have the ti bar being ti minus 1 is called Ito choice. The one where you take it in between the two time points is called Stratonovich. And I wanted with you now to go through the Ito choice. In that choice, if you look at the equations that we have on the slide, you can write it in a form where we have finite time intervals delta t as so. So this is the standard deterministic part with a drift vector. And you add to that the multiplicative noise term, where you have here the evaluation of the amplitude at time ti, and you use the Gaussian increment at time I plus 1. So later, then you evaluate this. So that means trajectory that accumulates random delta w's up to point time ti, doesn't know anything about the time increment at time later. So these are two stochastically independent variables, and that's why this has a particularly simple mathematical structure. First thing we have to worry about is how we do calculus in this context. So what do we mean with differentials in such a context? And for that, we have Ito's formulas, and let me derive them for you. So consider a function f of x, which has some nice properties that you can do derivatives, and it's bounded. And then let's look at a differential of x and t. Well, that's defined as the value of this function at some time dt later, at some increment dx later, minus the function at xt. And that you can write out by just using Taylor's formula. So this gives f prime at xt dxt. That's the first Taylor coefficient. The 0th order one cancels off, obviously. And then let's add here also the second order Taylor coefficient with dxt squared. And then there could be higher order terms. Now we plug into this equation the differential equation that we had for our stochastic differential equation. So that then gives you f prime of xt a of xtt times dt plus c of xtt dw of t. Okay, that's just copying what the differential in x is. And now what do we do with the second order term? We only want things that are of leading order. Okay, so I could put in here the term that's dt squared, but that's already higher order. I could put in dt dw, and you know dw is order square root of t. That's also of higher order. But the term dwt squared is of order dt. So I'll keep that. So c squared xtt dwt plus higher order terms, and this is dwt squared. All right. Okay, those terms I neglected. They're of order dt squared, dwt, dt, etc. Now, one thing I want to show you is this is the generalization of our simple Ito formula that we had. So remember, we evaluated this for a 1 here and got time. And now we want to evaluate this for a function g of tau, in the sense that I'm doing here a Ito integral. And the result of that is d tau g of tau from t0 to t. And that means that when I calculate those integrals, that indeed I can actually replace any square of my Wiener increments simply by a time integral. Let me show you now how this works. So we again, as in the simple case, we consider the mean square limit. So we ask, what is the mean square deviation of these two results? And show that the mean square deviation of the two results goes to 0 as the number of points goes to 0. So we look at delta I, which is the limit, the number of discretization points going to infinity. And I want the mean square average of the sum over all i's. And let me not write the indices here in detail. gi minus 1 delta wi squared minus delta ti. I want the square and the average, right? So I take the discrete difference of this expression and that expression and want the square of that averaged. And my task is now to show that this is going to 0. Good, now let's write this out. This is further equal to, and what I'm doing now is I'm separating those parts in the sum that are in the diagonal and those that are off diagonal elements. The parts in the diagonal, this is a sum over I, g I minus 1 squared, delta wi squared minus delta ti squared. Okay. That is the diagonal. And then I'm adding here, the 2 comes from counting, so I'll take only those terms here where I is less than j, and the 2 accounts for the double counting. And then I have here gi minus 1, j minus 1, delta wi squared minus delta ti, and the same thing for wj squared minus the tj, and I'll take the average here. Okay, now as you look at those expressions, you should see here that I is less than j, but more importantly here is I minus 1 is less than I, and j minus 1 is less than j. So these terms here, both of them, are statistically independent of that expression here. And that means you can draw in the average, so you average just this expression here at the end. And then you know what the averages are, because all you're averaging over is the Gaussian moments that you all know, because they're given by terms that are linear in t. And then it turns out when you do the math for this term here, you actually get identical to 0. What about the first term? Well, in the first term, the same argument holds here, that this here is independent of that. So I can take the average in here as well. Let me write that. So that's limit of n going to infinity, sum over I. Then, sorry, I can take here g I minus 1 squared, average. And I can take the separate average here of dwi squared minus delta ti, the square of that, and I average this. And you might recall this is the same thing as we did in the simple case before in the session this morning. So you get that the term here in the expression is 2 times limit of n going to infinity, sum over I, gi minus 1 squared times delta ti squared. Well, now I know that, actually I'm assuming that this function that I'm considering is bound. It doesn't diverge anywhere. It's always true in the systems that we study. So this is smaller than a bound that we have for this function g, some number. And importantly, so it's smaller than this times the limit of n going to infinity, and then we have n terms, and they all go like t over n squared, and that goes to 0. So we have shown that this converges. Okay, so upshot is that we can always do this if we consider an integral. And that means now, if I take the other formula, so df of x and t, just look at what we had there. This expression, we can replace that one here by dt. And that's my second Ito formula, means you get a f prime plus a half c squared f double prime dt plus c f prime dw t. So you see from this property of Ito calculus, you get a linear in dt contribution from the multiplicative term that you have in the noise. And that's the Ito formula together with the other one where dw squared can be replaced by dt. So now that we have that, we ask ourselves, given an Ito SDE, what is the Fokker-Planck equation that you can derive from it? So let's argue in the same way as we did when we derived the Fokker-Planck equation. Let's say we have a test function, f, and this is a well-defined function. In the domain, the random variable is defined, and I want it to be 0 at the boundaries. That's the property of this test function that we study. Well, you can then take this, of course, into the average. And now we use just what we had before, namely the Ito formulas that we just derived. Okay, this one here. This equation we now use. So we have df is this. That's what we keep. And this one, what about this one? I take the average is 0. Okay? So it's gone. That means the only term I do have here to first order is a, depending on its coordinates, times f prime of xt plus a half c squared xt t f double prime of xt and the average of that. Now let's write out the right-hand side, the left-hand side over a domain where the stochastic process is defined. Let's call this domain R. And let me write the process, the average, as an integral over my probability distribution function that I'm seeking to describe my random process. Well, this is the same here on the right-hand side, same domain R, integrate over x, p of x and t, and then in the brackets, a of x and t, f prime of x, plus a half c squared of x and t, second derivative of my test function, f of x. The right-hand side, we argued this before when we derived the Fokker-Planck equation in a different context, can be rewritten by partial integration. So you have here derivative acting on f. You make it act on the left-hand side, and you ignore the boundary term because we have assumed that f is decaying at the boundaries. Then this becomes a dx acting on p times a with a minus sign. And you do twice partial integration here, then you get plus a second derivative also acting on the left-hand side. Right? So pi, partial integration, gives you an integral over the domain. Then I have here an operator, dx, and let me write this now in shorthand notation. Oh. Okay, this is then f of x, and then I have minus dx, as I said, acting on a p, plus a half dx squared acting on c squared p. Since this is valid for any test function with proper features at the boundaries, this is valid for the integrand. So we conclude that, I forgot the time derivative here actually. So I conclude dt p of x and t is minus dx ap plus a half dx squared c squared p. That is the key result, the Fokker-Planck equation of this form, where you have the a here, the drift term, and the c squared there is the same. Okay, it's the same or equivalent to the differential equation, which is a dt plus c dwt in the Ito sense. You can do this both ways. This follows this direction, but also that direction. So given a Fokker-Planck equation that you determine by knowing the jump moments, for example, you can write down equivalent Ito calculus equation as a stochastic differential equation, or given such an equation in Ito sense, you know that the corresponding Fokker-Planck equation must be this. So it's completely mathematically equivalent. You can take either choice. That's key. It's mathematically equivalent whether you start from here or start from there. If you have good reasons to derive a Fokker-Planck equation, and you know a and c squared because you know the moments, then you start from here. And if you want to, say, simulate the equation, you can use the Ito calculus like so. Or you have some reasons to say, I actually know that my equation of motion needs to be in Ito interpretation. Then you can say, taking that, I can also calculate the Fokker-Planck equation. What about other interpretations? You could have also a Stratonovich interpretation. So let's ask ourselves, how do you go from Ito to Stratonovich and back? Key point now for you to understand is that xt is a given stochastic process given to you by the finances, by the physics, by the biology, and you want a description for that stochastic process, either in terms of an Ito form or a Fokker-Planck form or a Stratonovich form. And let's say for now that I have this already, that I know this is one way of representing my stochastic process. I can do it in terms of Ito or the Fokker-Planck equation. And now I'm asking what would be the equivalent form of exactly this stochastic process, the same one, in a Stratonovich form. All right, so let's ask, how would I write this stochastic process if I were to take on the right-hand side the usual terms XSS, but a new function A tilde, not necessarily the same as A, plus an integral where I put here an S indicating that I evaluate the stochastic integral using the discretization scheme corresponding to Stratonovich. And then I have here another function, C tilde of X of S. And I'm asking what is A tilde and what is C tilde in that formulation, so I get the same statistics as for that. So basically I'm asking what's the relation between A and A tilde and C tilde. Good, let's do the math. Let's first remind ourselves of what this stochastic integral in the Stratonovich sense actually is. It is defined as the continuum limit of a sum over a discrete set of points on the time axis, and I'm evaluating this at an intermediate point, so at half of the position between the 2 points times delta Wi. And as said, I want it to be of the Ito, I want it to be the same stochastic process. So let's write the stochastic integral more in detail. So, and forget about the sum for now, or the limit. Keep this in mind. I'm always meaning the limit. So let me rewrite this a bit. When you have this expression here on the right-hand side, you can evaluate this at xi minus 1. Have a question?
Yeah, I'm so sorry, I don't want to drop the sentence.
Yeah, please ask.
Shouldn't this be by the definition C of x of and now
yeah.
1 plus t2 divided by 2, and so this is kind of...
This is just a shorthand of this, and so if you write it as a half ti plus ti minus 1.
We average the time, not the x.
Yeah, and then you evaluate the corresponding x at this term, right? And then you Taylor expand the x, and then you basically get this.
Exactly, so we neglect some terms again.
We only want all these things to be in the smallest order of delta t or delta w. And therefore, this is equivalent. Yeah. So you do the sum. Well, I can do it for you if you don't believe me. So this is C evaluated at xi at x at a half ti plus ti minus 1, right? And this is x of ti minus 1 plus x prime times the delta t that you have here times a half, because you have the half of the time points. And that is the delta x I, because you have to evaluate this at xi minus 1. Okay? And that's what basically comes here out as well. So if I write this out, I get sum over I. Then I'm evaluating the ci tilde right here. And then I have plus a half times tilde at I minus 1 times delta xi. Okay? Because you're only interested in small deviations in delta xi times delta wi. Now we insert the E2 solution. Why can I do this? Because it's the same stochastic process. Right? I'm not dealing with a stochastic process that's different. It's the same thing. So whether I evaluate the delta xi in one or the other way shouldn't make a difference. So that's ai minus 1 times delta ti plus ci minus 1 times delta wi. And then we continue here these calculations. That's then the sum over I, c tilde I minus 1 delta wi. That's the first term that we have here, right? And then we do have here plus a half c tilde prime at I minus 1 times the delta xi. Well, we just insert what this is. This is ai minus 1 delta ti plus c I minus 1 delta wi times delta wi. Now, look with me at those terms. Delta w times delta w is linear in delta t. Delta w times delta t is already higher order. So I can neglect that one. And I'm remaining then just with this. So I'm remaining here. Now again, the limit n going to infinity. This here, the first term, is simply the E2 integral over c tilde xt and t. That's its definition. And the other one, using E2 calculus, is a time integral. Right here I'm using now that for an integral, I can replace this here by dt, one of the E2 formulas. This is also so an integral over dt of c of xtt c tilde prime xtt. Okay, now I just concatenate everything that we had. So if I were to write, sorry for putting this now on the bottom, but that's the best place. xt is then x0. Just look on the above. Then I'm having here the integral from t0 to t dt. And that's not just copy of what we have. We have the a tilde from above. And let me spare the arguments. So you get a tilde. And then you have this extra term that I just derived. That's also going into the time integral. So this is plus a half c tilde prime. And the final term is plus integral dw of s c tilde of xs s. Okay, and to be precise, I think I should here use S instead of T. Okay, now that we have this, so this is the differential equation that you can replace the Stratonovich equation with, but now you have what? You have a equation that's in the Ito form, like the one that we had. It's no longer on the board. It's basically this one. So we can just compare coefficients. What's the coefficient in front of the delta W? Here it's C, there it's C tilde. So that means I conclude C tilde is C. It's the same thing. It doesn't change. But the difference is that here you have an A, and there you have an A tilde. And they must be equal. So the A equals the A tilde plus a half C tilde prime. And now you're done. Now you have all the equivalences on the board. We have the Ito stochastic differential equation. We can transform the Ito equation into a Fokker-Planck equation with the terms A and C directly entering in front of the piece. If I want this in a Stratonovich interpretation, I can do so, but then I need to choose for the corresponding Fokker-Planck equation one where I replace the A by this expression, and I replace or keep the C to be the same. And now if you flip back into your notes, you will realize if you do so, then the Fokker-Planck equation we get from Stratonovich is the same as the one that you get by naive calculus. Good. Now let me summarize that, because that's really important. Okay, so let me give you the logic of all the things together. We do have, say, a stochastic process from which we can determine the moments. Let's say that's our starting point. Somehow we measured it. We have computer simulations or experiments that allow us to trace the trajectories, and we measure the jump moments A and B. If you measure those jump moments, you can immediately write down the corresponding Fokker-Planck equation, because it's defined by those jump moments with the coefficients A and B simply given in terms of those jump moments. And here it is. And you could say that's good and fine for me. I'm satisfied with relating jump moments that I measure or simulate with a theoretical description that I want. But now you say I want it also differently. I want it in the form of a stochastic differential equation. And then I just showed you that this Fokker-Planck equation can be written as a Langevin equation in the Ito interpretation, where the prefactor of the drift term is A, and the prefactor of the noise term is C, which is basically here the square root of this B. And you can also, that's also what we showed, you can rewrite this Langevin equation for the same stochastic process in terms of a Stratonovich differential equation. All you have to do is you have to change the drift term. So you get what's called a spurious drift term here in this equation. And that's also equivalent. It's just another way of doing it. You just have to recall that then this object that you're calculating here has to be interpreted as a stochastic integral in the Stratonovich sense. And you can go back and forth. So you can go from all the directions that you have, and it's your choice. Say you know this, you can write it like Ito, you can write it as Stratonovich. Say you have this, you can go along the way as you like. This is a matter of mathematical equivalence. It's not a matter of physics. It's really just a matter of the math being the same if you express things in proper drift and diffusion terms. So where does the physics come in? Well, the scientific problem will then tell you where to start. If you have this, that's something I alluded to already, then you have the Fokker-Planck equation immediately. If somebody says, well, I somehow know that my stochastic dynamics has to have Stratonovich interpretation, whatever the reason for this is, and I do know my drift term that I measure or know in this Stratonovich interpretation, then that's your starting point. And you can use that to derive a corresponding Fokker-Planck equation if you like, or rewrite it in terms of an Ito because you find this more convenient to do simulations. But there is a point in this equivalence of mathematical formulations where you have to put in the science of the problem that you study. And it depends on your starting point. Questions? Clear? Okay. Yeah.
So, for example, the Ito Langevin equation, or whatever Langevin equation we write here, is fueled by the Brownian motion behind, right? So if we were to sample some trajectories, this kind of Gaussianity is somehow encoded in the movement we observe, right? But on the other hand, if we maybe look at the experiment, where we got the jump moments from, this does not need to be the case, right?
No,
doesn't need. Sort of information we lose in this.
Yeah, so it's true. So a real physical process will not be white noise. Will never be. White noise is a very mathematical abstraction of what the actual stochastic process is, because it does have these infinite correlations, infinitely small correlations in time, which is not realistic. Actually, there's always some kind of finite correlation time. And then the question you have to ask is, what are the other time scales in your problem that you want to study? And is the time scale you're interested in above or below the time scale where you have correlations in the noise? If your time scale that you want to study is above that time scale where you have correlations in the noise, then you're typically safe to ignore the time scales in the Gaussian process, in the stochastic process, and idealize it as a Gaussian white noise.
So in principle, if you simulate trajectories with the Ito, they don't have to look like in the experiment, really. Like there's this small difference.
Well, what it means. In experiment, I have a time resolution. Yeah. That means, my instrument is slow or fast. That's one problem you have when you do experiments. Even if you have perfect time resolution, then it depends on what you measure exactly at what time scale of the process that you're interested in. So like a molecular motor running along a microtubule, you might want to be interested in the motion of the proteins itself. Well, that's different physics. If you're interested in the randomness of the position of your molecular motor along the microtubule, well, then you're closer to something that you would describe by such a model.
So one has to choose the time scale such
yeah.
that this Brownian picture is valid.
Let's put it the other way around. You have a physics problem, a science problem, where you're interested in the dynamics at a certain time scale, and then you start studying the physics at that time scale. And then you ask yourself, what do I know about the system in terms of deterministic dynamics? So what are the forces, what are the potentials, things like that. And then you have to argue of what your noise is. And that's a very difficult point, because there's no a priori way of saying what the noise is. And that's where the science of the problem comes in. So you cannot say Ito is right or Stratonovich is right. It depends on what you study and what time scale you use. The way you would approach these kind of problems is typically that you say you try to take all the relevant degrees of freedom into account, meaning all the slow variables that really describe the system, and then make a leap of faith, saying that all the other degrees of freedom that you ignore can be summarized by a white noise with a certain amplitude. And that's an assumption then that you make. And the quality of that assumption depends on, what other variables you choose to describe your scientific problem.
Yeah, because that white noise is hard-coded in the Langevin.
It's hard-coded in the Langevin equation, and it's the awkward mathematical object. And the awkwardness of the mathematical object, shows in the E2 calculus that you do. And the Stratonovich, right, this was the naive thing you get when you have ordinary calculus. And if you have reasonable correlation times, then there's nothing like Gaussian white noise in the system. It's all smooth and regular functions. And once you have smooth and regular functions, you get away with ordinary calculus. You don't have to worry about a particular calculus where dw squared is dt, because that's a feature at this small time scale of the idealization of the process as a Gaussian white noise process. Okay? So, scientific problem, you need to think hard before you write down an equation for the problem you want to study.
Is there any scientific problem by changing the time scale you are looking on? It changes from E2 to Stochastic.
It doesn't really change because the formulations are equivalent. So I would say if you change the time scale of question you ask, then you have to ask yourself, what is the proper description that you want to use at that time scale? And then it may matter what kind of variables you choose. Right? The coarse graining of a physical process is not just looking at different time scales, it's often also looking at different sets of variables, and they may change as you coarse grain from a smaller to a larger time, or a smaller space to a larger space region. Okay. All right, break here.
The physical problems, f functions we are talking about here don't have any meaning.
It would be an observable. So you could say, I want to calculate the average of x, so f would be x. Or you can say you want to calculate some function of x, same thing. And it's a mathematical tool for me to derive from the equation for f, a equation for the probability density. That's just it.